So our last one is our t-distribution, which basically, kind of fun history about this is it's very much like, how do I say this? Like we have the idealized version of like how something works. For example, we love to have everything as a bell curve, but in reality, not everything is a bell curve. So one thing we can do is basically, or at least what William Gossett figured out, is a way to estimate something that looks like a bell curve. And he calls it the student's t-distribution. Fun fact, the reason why we call it the student's t-distribution and not like the Gossett distribution or something like that is because he actually worked for Guinness Breweries. Guinness, yes, the same beer company as today, in 1908. And basically he figured out, he was a statistician, he kind of figured out a better way to brew beer and like, you know, statistically like moving in the how much ingredients and stuff like this. And he actually came up with the system. But Guinness basically said, you can't publish it under your name because you work for us. So he published it under saying it was a student's work. So it's kind of funny is that's why we call it student's t-test. Kind of interesting fact. Anyway, this t-distribution basically is when we don't know the actual probability distribution. So kind of going back a little bit with what we were just discussing is that a lot of times you would measure the actual, world, right? And see what happens. And that would be your ground truth. But sometimes you don't have the luxury of actually taking the full, you know, for example, like the full census of everyone in the United States and know exactly, you know, how many people like blue over red. Like, well, that's just not something you know. So we can basically use a t-distribution to estimate that distribution since we don't know the full population. So you'll notice that it's really similar to like a normal curve, a bell curve, but you'll see that it has these like, what's it called? These like heavier tails going through. So you can see here in this blue is our bell curve, okay? And you can see progressively going forward. And our degrees of freedom, which I'll kind of define this a little bit more, essentially it's just how many ways our data could vary. So remember, like if I took one data point, I don't really know if I got the actual average or if I got something that's closer off to the tail. So in all likelihood, I most of the time will measure things right in the middle, but sometimes I might measure something off to the side here. So basically our degrees of freedoms help measure saying, well, if I have these actual measurements, and it's like, well, maybe they just by chance are all off a little bit to the left, or maybe they're all off a little bit to the right, or maybe the standard deviation is a lot wider. So basically what happens is when you don't have as many data points, less degrees of freedom, you essentially have, say, well, I have to consider maybe the edges here are a little more likely than I expected. And that's why these tails have a little bit larger value. So you can see, like, we call them like heavy tails. So you can see here they're a little bit larger than the normal bell distribution. But as we get more and more data, right, as we get more and more increased degrees of freedom, we actually approach closer and closer to the actual bell curve, normal curve. And you can see here, the red, I think, no, the red is the most frequent one. So that degrees of freedom, this red right here, is getting closer and closer. This green is the prior one. And you can see as we increase to 3, 5, 10, 30 degrees of freedom, that green bar is getting closer and closer to the point where there's 30. It's pretty close. You can barely see that red on blue. It's pretty close to the normal curve. And this is actually where it comes from. You'll hear people say, we need to have at least the number of samples has to be greater than or equal to 30. This is where this comes from, is that basically at 30, we have something that approaches the t-distribution itself. Okay, so that is the t-distribution. So with that t-distribution, we can actually do something similar with the t-statistic and actually something like with the z-score. So what's nice is I'll kind of do a little walkthrough, and a lot of this is already built into our statistical packages. So you can see here, I'm using SciPy stats, okay? Instead of like what we used before, OLS. So we're using SciPy stats here. Basically, I can give it a confidence interval like what I want of 95. And you can see here is that basically it's saying, okay, well, I have this, let me see if I should read this myself real quick, is that I say, okay, let's pretend our sample mean should be 65. So you can imagine I have a bunch of data, I collect all of it. Usually our degrees of freedom is equal to the number of data points minus 1. So if I had 100 data points and I say, okay, I have these 100 data points, I collected this information, the sample mean is 65, right? Whatever that is, right? And then my standard deviation is 18. So that's for my specific data set, right? And then I say degrees of freedom is 99 and say, okay, but I want a confidence interval of 95. I say, okay, to get to 95%, what is the actual average? And the average has to go between 29 to about 100 right here. If I have more data points, if I have less data points, if I only have 9 data points and I have the same exact averages, same average, same standard deviation, okay, to get a 95% confidence interval, saying like I'm basically confident 95% of my data points would fall within this average, this window will get larger. So we'll see it slightly less than 29 and more than 100. And you can see here, you can see it gets a little bit wider because basically it's like, well, we don't have many data points, so we don't know for sure if it actually falls within that range. If I have like this many going something like that, then we can see it goes closer and closer. And if our standard deviation was closer to like 1, for example, you can see basically our actual average, our population average, likely 95% of the time would be, it's 95% confident that it would fall between 63 and about 67. Okay. Does that make sense to you people? Seems some little faces being not so sure. Any questions?
Yeah, I do one. Sorry.
No, it's fine.
Questions. Wouldn't that vary according to the total population you're surveying, like you're trying to understand?
Right, and this is where you're assuming the population is much larger than the sample that you measured. So this is kind of like if you want to measure all the people in the world, you know, obviously there's some things you have to deal with that because, you know, people are different, but let's just say all the people in the world and you want to see like the height of the average person, right? You would randomly pick out from, you know, different places throughout the whole world, right? And you might get, you know, only, let's say 30 people. And it's like, well, okay, our population, our sample size is much smaller than the population, but we can still actually get close to a bell curve distribution based on the t-tests. And so I know it seems kind of counterintuitive, like how can you like, you know, how with only like 50 people or 100 people of like 1 billion people can you actually get close to that point? And it basically comes down to the fact that one, your sample has to be randomly collected. It has to be random. If there's bias in it in the sense that like it's not the full population or your sample only includes parts of the population, then you can't assume those kind of things. But for the most part, if you can assume the population is a full thing and that your sample is actually representative of the full population, you can actually use this to basically estimate what the population really should look like. Okay. Yeah. Again, this is where like, it's, to be honest, I think you're right to question it. Being like, that doesn't seem like it's like you should be able to do that. It's a very like, I think for the long, like, again, I'm still kind of flabbergasted when I hear, you know, a sample size greater than 30 actually can do a pretty decent job. But it actually, you can show that it basically estimates along here. And part of the reason why is because we are sampling over, when we do a confidence interval, is a little subtle point. And honestly, it might be a little more confusing, so just bear with me. But when we do a confidence interval, basically we're saying of our sample, we pretend we are grabbing our sample and going over and over and over again. And for example, we might pick the most infrequent thing in that in our sample, and maybe that could be the actual average, or it could be on the very other side of like the most, you know, the maximum value. For example, maybe our value is like the most is 100 and the smallest value is like 20. And so we could possibly pick like out of 30 times, 20 over and over and over again. What's interesting though, because of the central limit theorem, which is basically say if you do a sample over your sample, you approach a bell curve. And that's essentially what's going on here, is that we can essentially say, well, if our little sample is representative of our whole population, we can basically assume, well, a sample, like us doing a little mini experiment, which is what the confidence interval really is, of using their sample to build that up, would be representative of the population. So we can actually build up and say, well, okay, that means we can be pretty confident on where our sample or where our population average or mean really lies. And that's why, for example, if you have very few of them, your confidence interval will be much larger, versus if you have a lot of them, your confidence interval will get a little bit smaller. You can only get it so small though, because there's a certain point where you don't know if you collected just by pure chance things that weren't supposed to be in there. Okay. Cool. Did that help explain a little bit? I know that's, okay, I know that's, I feel like I had this picture in my head and I feel like I'd like to draw it out, but I can't draw it perfectly here. But that's kind of like what confidence interval is going through. And that's why we can do this. So kind of show you a little bit like this looks like is we have some sample. I'm just making some random data. So in this case, let's go ahead and use 500. So I'm gonna get 500 people. Let's start with 50. Okay, so I have 50 people. I'm saying an average of 54, standard deviation of 17. These are just some random numbers I picked out. So let's see if I can actually quickly do it. Well, okay. If we have this part right here, if I show you really quickly what this looks like, you can see here, for example, just get a feel for like what the data looks like. You can see here like 33 is pretty small, but it can go all the way up to like, we see 74, around here. So there's some even 83. So some are really large, some are really small. But for the most part, they're going to be centered around 54. So if I, for example, do samples.mean, you'll see it's hopefully around 54. Okay, and you can see standard deviation. Okay, it's about almost 17. Okay, and so we have this data set, we have our 50, so you can imagine I grab that out of the population, okay? And then, for example, what I can do here, I'm smart, I actually showed it ahead of time. So you can see here the distribution of the people who are here. So you can see like this roughly normal in here, and we can actually compute then our confidence interval with the t statistics or our t distribution. So we can say, okay, well, we want a confidence interval of 95, right? Our degrees of freedom is basically the number of samples minus 1. Here's our samples mean, which we saw was about 54 point something. Our sample standard deviation was a little bit under 17. And we run this now, and we can actually see that means the true population, we have a 95% confidence that our true population will fall between about 21 and 89. Okay. So that means basically is that if we do this over and over again, 95 of our experiments would fall, 95 out of 100 experiments would fall within between 20 and 89. So I think that sounds like a pretty reasonable kind of thing. If you increase this number, okay, so for example, well, let's say I decrease it, that's probably more relevant. If I only decrease it to like 5, okay, and you can see here, we have our standard deviation, we can still do our t-statistic on here. And you can see here the average, in this case, if I actually look at the average, about 50, so it's much smaller, right? And our standard deviation is actually much smaller too, just by pure chance. And we can see here our interval that went from 21 to 89 for our, with our first sample of 50, we can see here that we have to have a larger interval in order to capture our true population mean, okay? So this is kind of like how you can basically do a sample, you collect a sample, and you wouldn't literally generate this, it's just me generating it. You would collect your sample from live data, and you can estimate then what the likelihood of that sample representing your true population. All right, cool. Sound good? Any questions? All right, well, cool. So I'll go ahead and stop it here.